Hello. Welcome to the Sleepy Alchemy channel. If your mind is still active, still thinking, let's give it something gentle to focus on tonight. Something slow and steady. Tonight, there is no need for you to do anything. Tonight, there are no tasks for you either. There is nothing you need to complete, understand, or anywhere you need to arrive. Just being here is enough. The weight of your body, all of these are completely in place right now. Tonight, only one thing is required, to rest, and the rest will happen on its own. Think for a moment. The substance I will talk about tonight was formed millions of years ago, just like glass itself. It emerged from inside a volcano, cooled down, solidified, and quietly found its place on the face of the earth. Tonight we will explore that substance, but without a rush, slowly, like a stream. As scientific research shows, the human mind needs low-intensity but interesting information rather than complex thought in order to calm down. The mind gently tethering itself to a single point separates it from the pace of daily life. Tonight, that point is volcanic glass, namely obsidian. This black material that comes from inside the earth, plays with its light, and makes its coldness felt when held by hand. Wherever you are, staying there is enough. Your bed, the couch, the floor, it doesn't matter. The weight of your body is already in place. This weight is not from fatigue. It is simply the gravitational pull of the earth upon you. This pull has existed for billions of years. Your body, your cells know this. It is enough just to let yourself relax. If you enjoy videos like this, you're welcome to support the channel with a gentle like and subscribe if you'd like to return. When hearing about obsidian for the first time, many people imagine it simply as a dark stone, but technically it is not a stone. According to current geological classifications, obsidian is neither a mineral nor a crystal. It is volcanic glass. That is, it is an amorphous structure formed as a result of elements like silicon, oxygen, aluminum, iron, and magnesium rapidly emerging from inside the magma and cooling. The word amorphous comes from Greek, meaning formless, that is, lacking a crystal lattice. However, this formlessness does not make it weak. On the contrary, this characteristic gives it a unique beauty and structure. The atoms inside crystal minerals are arranged in an orderly, repeating lattice structure. Quartz, salt, and diamond are like this. But obsidian is different. The atoms inside it solidify irregularly during rapid cooling. And rapid cooling brings about something unexpected. The atoms cannot find the time to move and align into order. They freeze like a momentary snapshot of their flowing state. For this reason, as some say, obsidian is a frozen liquid. Of course, this expression is not entirely scientifically accurate because the difference between liquid and solid is more nuanced. But this metaphor beautifully explains its essence. It is within a moment of time. The history of glass dates back long before human history. According to available scientific data, materials of obsidian origin were used at least 2 million years ago. Obsidian tools have been found in archaeological excavations dating back to the Homo erectus period. These ancient people had discovered the unique characteristic of this material. When obsidian breaks, it forms a conchoidal fracture, that is, a smooth, curved edge like a rippling water surface. This edge can be very sharp, so much so that, compared to modern surgical scalpels, obsidian knives can produce a finer cutting edge in terms of some measurements. Although studies on this topic note that this comparison is not true in all contexts, the cutting property of obsidian has been highly valued historically. However, the most interesting aspect of obsidian tonight is not its sharpness. What truly fascinates us tonight is its relationship with light. What happens when light passes through something? Despite this question seeming simple, its answer reveals one of the most beautiful corners of physics. According to current understanding of physics, light travels at a constant speed in a vacuum, approximately 299,792 kilometers per second. This number is so large that the mind slows down a bit while trying to comprehend it. It takes an average of 8 minutes for light to reach the Earth from the sun, and this means that the sunlight we see every day, that transparency filtering through our window right now, actually existed 4 minutes ago. Seeing is always looking into the past. But what happens when light enters glass or any transparent substance? Its speed slows down. This is called refraction in physics. Depending on the wavelength of light, its speed slows down to different degrees. This means that when white light passes through a glass prism, it separates into its color components: red, orange, yellow, green, blue, purple. The rainbow is the result of this mechanism on water droplets in the atmosphere. Because obsidian is glass, it refracts light in the same way, but it transmits very little information. Obsidian is usually black or dark in color because minerals inside it, like iron oxide and magnetite, absorb the majority of the light. Even so, the edges of obsidian transmit light. When holding a thin piece up to the light, the edges shine with purple, blue, and green colors. Despite this being scientifically explainable, anyone who sees it knows that its effect on them is completely different. Think for a moment. Everything next to you tonight, the wood of your bed, the paint on the wall, the glass of the window, all are made of atoms. However, not all these atoms are the same. Some were at the bottom of the sea hundreds of millions of years ago. Some came to Earth with meteorites. Some, like those inside obsidian, were melted and mixed in the magma of a volcano, and then found their current structure as they cooled. According to current astrophysical models, silicon is formed as a result of nuclear reactions occurring inside stars. This process is called nucleosynthesis. Later, those elements spread into space and over time become part of the composition of new planets and rocks. Meaning, the silicon atom inside obsidian has its own story. Perhaps it came from the center of some star. The available data does not fully answer the question of which star it came from. Nevertheless, the question itself is beautiful, even without an answer. The rhythm of your body is already in its flow. Although this rhythm slows down a bit during rest, it is normally 12 to 20 times per minute. Your heart beats on average 60 to 80 times per minute. All these processes happen outside of your control. Your body knows what to do. Obsidian, on the other hand, is now simply somewhere, in a museum, in the soil, on a researcher's desk in its current state. It too, just like you, is simply within existence. It does not have to do anything. The atoms inside it work in an organized manner, store energy, and protect chemical bonds. But it does this without any choice or selection. It simply flows within the framework of the laws of physics, like water flowing down a slope, like light reaching towards a source. Sometimes the mind transitions from one thought to another. Even if it seems causeless, this is actually a process where the brain searches for its own order. You think about obsidian, then suddenly the peak of a mountain comes to your mind, then snow, then the coldness of water. These associations turn off a motor that has tired the mind. One is turned off, one is turned on, but none is ever fully closed. As psychological research shows, especially in the pre-sleep stage, when the mind processes low-frequency objects of interest, brain waves called alpha waves increase. These waves indicate a state of rest, but they are in the stage before transitioning to sleep. According to some research, trying to completely empty the mind may not yield the same result for everyone. Some research notes that directing attention to light objects at this stage might be associated with a calmer flow of thought. Like magma flowing from the mouth of a volcano, you can continue without rushing, without stopping. We can say that magma never rushes. This melted material inside the Earth's mantle, sometimes for years, sometimes for thousands of years, stays in the same place, under pressure, under heat, kilometers below the surface, at a depth the human mind cannot fully encompass, but invisibly. Then one day, in a geological timescale, it means one day, that is, maybe centuries, maybe millennia later, a crack opens, a weak point is found, and the magma moves slowly, thickly, and heavily. Tonight we are inside that movement. We are inside that process, which we never see, but which exists under every stone, every soil, every mountain. Your body is now lying on the ground. We can say that your body is actually on the earth, and beneath it is that hot, quiet, moving layer. When looking at the chemistry of magma, the first thing that attracts attention is silicon dioxide, SiO2. This molecule constitutes a large part of the Earth's crust. According to current geochemical data, approximately 46% of the Earth's crust by mass is oxygen, and 28% is silicon. These two elements together form the basis of silicate minerals: quartz, feldspar, mica, amphibole. These are the most widespread mineral groups on Earth. However, the amount of silicon inside the magma fundamentally changes its behavior. Low silicon basalt-type magma is fluid. It creates widely spreading lava flows like in Hawaiian volcanoes. As the silicon amount increases, the magma thickens. its viscosity increases and it becomes explosive under pressure. Obsidian, on the other hand, is formed from high silicon magma, from the type called rhyolite. When this magma flows like lava, the gases first come out of it and leave, and then the lava cools. If the cooling happens fast enough, when flowing into water, when exposed to rain, or in conditions where the air is cold, there is no time to crystallize. The silicon dioxide molecules freeze in an irregular, amorphous structure, and the result is obsidian. How fast must this process happen? Current petrological studies show that for the formation of obsidian, cooling can happen within seconds or within a few hours in rapid cooling conditions, such as lava flowing into water. At this time, the lava surface turns into glass. However, because the inner part is still hot, it cools at a different speed. Sometimes, as a result, when looking inside obsidian, various layers, color differences, flow lines, and sometimes round cavities created by gas bubbles inside it are seen. These are the traces of that ancient flow, the snapshot of the moment the magma moved. When holding a piece of obsidian up to the light, sometimes it is possible to see these flow lines. Gray-colored lines stretch on a black background, as if it is an aerial photograph of a lava river. These lines have stood there for more than millions of years, under the soil or inside the rock, in a place outside the flow of time. No one has touched them. Let's look a little closer at the molecular structure of silicon dioxide without rushing. One silicon atom forms a bond with 4 oxygen atoms. These 4 oxygen atoms create a tetrahedron, that is, 4-faced structure around the silicon. Imagine one atom in the center, 4 arms extending in 4 directions, and oxygen at the end of each arm. This structure is called an SiO4 tetrahedron. And all these tetrahedrons inside the glass are connected to each other, but irregularly. One directed that way, one this way, resembling a system, but creating a network in a way that lacks the precision of any crystal lattice. This irregularity creates the main characteristic of glass. It transmits light of a certain wavelength, but not like a crystal where atoms are orderly. Light passing through the glass passes through this amorphous network. Sometimes it slows down, sometimes it refracts, sometimes it is absorbed. And the result is luminous but deep, transmissive but not transparent, that familiar glass appearance. The black color of obsidian is a separate topic. As we noted above, this color mainly comes from iron oxide. However, obsidian can be multicolored. In rare cases, green, sometimes dark red, and sometimes there are types called rainbow obsidian. The microscopic magnetite crystals inside it reflect light in such a way that burnt yellow, orange, green colors play on the surface. This phenomenon is called iridescence. It is the result of light passing between thin layers and creating an interference effect. Think of the colorful flashes in a soap bubble. The mechanism is the same, but this phenomenon is inside a million-year-old volcanic process. Everything begins at some moment. The temperature rises at a point inside the Earth. Maybe tectonic plates rub against each other. Maybe there is a region called a hotspot under the crust over the mantle. According to current geophysical models, these hotspots indicate the places where heat flows from inside the Earth gather on the surface. The Hawaiian Islands, Iceland, Yellowstone, All of these are over these hotspots. Magma moves upwards. Sometimes it flows rapidly through the main channel inside the volcanic cone via lava tubes, and sometimes it seeps slowly along cracks at a speed the human eye cannot see. The speed of this flow determines the final structure of the obsidian. Fast flow, fast cooling, a more amorphous structure. Slow flow, a longer crystallization time. Sometimes as a result, materials like semi-crystallized pitchstone or pearlite are formed, not pure obsidian. But pure obsidian, that deep black colored one, having a smooth surface, catching and holding light on its edge, is the result of quick cooling. Quickness is not a flaw here. Quickness is a condition of perfection here. There was no time, the crystal did not form. Because there was no time, everything froze in the state inside the flow. Sometimes the human mind also freezes at such a moment. During the day, it flows so fast that it passes from one thought to another, from one task to another, from one word to another. And night, precisely at these hours, is the time when that speed decreases. The mind does not freeze, but it slows down. In studies, electrical activity called alpha waves is often observed in this stage. Thought associations become wider, freer, less logical. This stage is described in literature as the hypnagogic state, the transition stage between wakefulness and sleep. Scientific research shows that this state has a strong connection with creativity. Edison, Tesla, Salvador Dali made statements regarding their conscious use of this state, but these claims are not fully documented. Whatever the case, this moment of transition is a real state. Like light standing on the edge of obsidian while the body sleeps, the mind still stands on an edge. This moment of transition is a calm and natural stage. There is no need to rush. One thing inside the magma always attracts attention: gases. Water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide inside the melted rocks. These are dissolved into the magma under high pressure. As the magma rises and the pressure decreases, these gases start to come out like an uncorked champagne bottle. This process is one of the main mechanisms of volcanic eruptions. However, for obsidian, those gases come out and leave before cooling begins. Left behind is the pure, dense structure of silicon without gas cavities. But sometimes not all the gas can come out. When looking inside obsidian, small round cavities are seen. These are the traces of those gases. Millions of years ago, a gas bubble inside the magma found its place there. Then every side of it froze and solidified, and the bubble remained together with the cavity inside it. This cavity is now there like a small room inside a rock, like a cavity inside a box, preserving history that no one has opened. Tonight, your breath is also in such a rhythm. Entry, void, exit. The silence between the beats of your heart is not chaos. It is expectation. It is the preparation for the next beat. The cavities inside the obsidian are also in such an expectation. There, since the moment the magma solidified, it waits. It waits for nothing, but it exists. Maybe this is the simplest form of existence. It is not an empty space, actually. It is a full empty space. The air atoms, nitrogen molecules, argon atoms inside it, these are suspended there, protected from the rock, defended from time flowing over it. Tonight, the body also switches to its natural rest mode. Everything is in its place. Light never travels straight. That is, it does in a vacuum. In that empty, matterless space, light propagates along a straight line. But when it reaches any matter, water, glass, air, obsidian, something happens. Light slows down. It changes its direction. It is as if it took a step and stopped, withdrew into itself, then moved again, but no longer in the previous direction. This phenomenon is called refraction in physics, that is, refraction. This word of Latin origin means to break back. It is as if light breaks when entering matter. But this breaking is not an ordinary breaking. There is a law here, an order. This relationship, called Snell's law, was formulated in 1621 by the Dutch mathematician Willebrord Snell. However, the exact same relationship was investigated earlier by the 10th, 11th century Arab scientist, one of the founders of optics, Ibn al-Haytham. Science itself flows like this too, from one person to another, from one century to another, from one language to another. Snell's law is not just a formula, it is the mathematical language of light's behavior inside matter. But tonight, we want to see that behavior itself more than the formula. When you project a ray, a narrowed beam of light, into a container full of water, what happens? When it reaches the surface of the water, if the ray is not at a perpendicular angle to that surface, it changes its direction as it enters the water. Why? Because the speed of light's movement in water is less than in air. According to current physics understanding, this speed difference results in one side of the wavefront slowing down before the other. The wavefront bends, the direction of light changes. To beautifully visualize this process, a thought experiment. Imagine a wide marching group of people, a line, stepping side by side. Everyone is walking at the same speed. What happens when this group transitions from a meadow to muddy ground? The first one stepping reaches the mud, slows down, but the remaining part is still on the meadow, continuing at the original speed. As a result, the line bends. Light is like this too. When a part of the wavefront enters the matter, it slows down. The other part is still in a vacuum. As a result, the wave bends. Now let's return to obsidian. The refractive index of obsidian, that is, the ratio of the speed of light in obsidian to its speed in a vacuum, varies between approximately 1.48 and 1.51 according to current measurements. What does this number mean? If the speed of light in a vacuum is taken as 1, the light inside obsidian travels at approximately 1 over 1.5 of this speed, that is, 2/3 of it. This is not very slow, but there is a difference, and this difference makes a difference. For comparison, the refractive index of water is approximately 1.33. Ordinary glass is around 1.5, and diamond is 2.42. This high refractive index of diamond causes the light entering it to bend very strongly, change its direction, and reflect many times inside, the phenomenon of total internal reflection. This process creates that familiar sparkle of the diamond. Obsidian, unlike diamond, absorbs a large part of the light. Iron oxide molecules absorb the wavelengths of the visible spectrum. But at the edges, in thin parts, a little light passes through, and this passing light refracts, separates into colors, sometimes creating that beautiful purple-green edge shimmer. Let's talk a little about the spectrum of visible light without rushing. The human eye can see a very small part of the electromagnetic spectrum. According to current physics data, visible light covers wavelengths extending from approximately 380 nanometers, violet color, to 700 nanometers, red color. What is a nanometer? It is 1/1000th of a meter. So the wavelength of the light we see is thousands of times smaller than the width of a hair strand. Why are these wavelengths important? Because the refractive index is not the same for all wavelengths. Glass, including volcanic glass like obsidian, refracts violet light more than red light. This property is called dispersion. When white light passes through a prism, this dispersion becomes visible, the color sequence of a rainbow. Violet on one side, red on the other side, and the entire visible spectrum in between. Obsidian does not separate light in this way, because it does not let a large part of the light pass through. But the rules of physics are within it. It absorbs light, reflects it, sometimes refracts it as much as its amorphous structure allows. This structure is irregular, but it is physics-less. Every atom is in its place. There is no crystal lattice, but chemical bonds exist. That irregular network of silicon-oxygen tetrahedra controls light in its own unique way. So what does the decrease in the speed of light mean? Speaking in a deeper sense, according to current quantum electrodynamics models, the slowing down of light inside matter is not actually the slowing down of light itself. In deeper descriptions, according to quantum electrodynamics models, the slowing down of light inside matter should not be understood as the stopping of photons. The electromagnetic field interacts with the electrons in the atoms of the matter, and as a result of this interaction, the phase of the wave changes. As a result, the speed of energy propagation within the matter appears different from its speed in a vacuum, but this does not mean the fundamental speed of light has changed. This explanation seems somewhat paradoxical. But this is also the most interesting point of science. There is always a gap between what appears to be and what is. Deeper questions are needed to fill this gap. And deeper questions can exist even without being answered. Keep such a question with you tonight. It is not necessary to solve it. Just be together with it. The reflection of light is also a separate physical phenomenon. It should not be confused with refraction. Refraction is light entering matter. Reflection, however, is light reaching the surface of the matter and turning back. Both phenomena happen at the same time. When a light ray reaches glass, a part of it reflects, a part goes inside and refracts. This ratio changes according to the refractive index of the matter, the angle of incidence of the light, and the wavelength of the light. For obsidian, this ratio is interesting. A smooth, polished obsidian surface can reflect light like a mirror. Obsidian pieces discovered in archaeological excavations are thought, according to current historical data, to have been used for mirror purposes by some cultures. It is discussed that obsidian pieces found from the Çatalhöyük archaeological site in the Anatolian region are suitable for this function, but the available data does not provide a definitive conclusion to fully prove this use. Such archaeological questions often remain open. Open questions are also a part of science. The third form of light's interaction with matter is absorption. A part of the light reaching a matter reflects. A part passes through, and a part is absorbed. During absorption, the energy of the photon is transferred to the atoms of the matter. The atoms vibrate with that energy. They become warm. Black-colored objects absorb a large part of the light. For this reason, in sunny weather, black clothes become hotter than white ones. White-colored objects, on the other hand, reflect a large part of the light. Obsidian, because it is black-colored, absorbs a large part of visible light. This absorption mainly comes from iron ions, magnetite particles. But in the infrared spectrum, that is, in wavelengths the human eye cannot see, obsidian behaves differently. Current spectroscopy studies show that the absorption pattern of obsidian in the infrared spectrum can be used to determine its volcanic source. This technique has been referred to in various archaeological studies, along with obsidian hydration dating, to understand the origin of the material, the trade routes. So, obsidian is not just a stone. It holds a signature. From which volcano it came, at what temperature it was formed, which elements it gathered inside. All of these can be read with spectroscopy. The light inside the matter makes the matter itself speak. Tonight, your body is also making its own unique light emission. According to current biophysics data, the human body emits infrared radiation, thermal radiation. All objects emit electromagnetic radiation corresponding to their temperature. This is a consequence of the Stefan-Boltzmann law. For the human body, the peak wavelength of this radiation is in the infrared region. It is invisible to the eye, but it exists. Night vision cameras are designed exactly to detect this radiation. So tonight, you are also emitting invisible but real light. This energy coming out of your body, like magma coming out from inside the earth, mixes with the air of the room from the inside towards the outside world, slowly spreads, cools down. Obsidian gains this structure as a result of rapid cooling. While talking about the refraction of light, it is impossible to skip one topic: total internal reflection. Total internal reflection. When light inside a matter reaches its surface from a certain angle, it is totally reflected. It cannot get out. This phenomenon occurs at angles greater than the critical angle. This is exactly the working principle of fiber optic cables. Light passes through a thin glass fiber. It is totally reflected at every surface, traveling a long distance without losing any energy. Obsidian demonstrates this property in a different way. When light enters obsidian, it reaches internal surfaces, crystallization nuclei, magnetite particles, the irregularities of the amorphous structure, many times. Every time a part of it reflects, a part is absorbed. As a result, a large part of the light stays inside. It is absorbed, turns into thermal energy, slightly heats the obsidian. This heating under sunlight is very small, but it exists. Obsidian is slightly warm in sunlight because it takes the energy of light inside itself. In ancient times, this property was not known, but it was felt. When obsidian is kept in the sun for a while, it is not cold when held by hand, but relatively warm. This warm touch, this small heating effect, is a result of the absorption of billions of photons. The energy coming from the sun is inside the matter coming out of the volcano. The two have come together on the surface of a volcanic glass. Now you are breathing in and out. The oxygen atoms inside that breath were in the air of the room a little while ago. Before that, maybe they were in a leaf of a tree. Before that, maybe somewhere close to the surface of an ocean. All these atoms are in motion, but in this moment, in this breath, they are inside you. Then they will be released. They will mix with the air again. They will be a part of another story again. The silicon atoms inside the obsidian, however, are motionless. For millions of years, they have been nailed to their places with chemical bonds at a node of the amorphous network, without moving, waiting. It waits for nothing, but it exists. To exist is also something. Perhaps the simplest thing. A piece of stone can travel the world. This idea seems strange when first heard, but archaeological data has shown this repeatedly. Obsidian has traveled tens, sometimes hundreds, sometimes thousands of kilometers, traveling roads by passing from the hands of people to hands, flowing through trade routes, being passed from one generation to another. This stone was neither as heavy as gold nor as light as cloth, but it was worth carrying, because obsidian could do one thing that other materials could not. It cut. It cut with such a sharpness that, considering the conditions of its time, this material was a valuable technology. But tonight we want to trace its movement, its journey in human hands, more than the sharpness of obsidian. This journey opens one of the most beautiful branches of science, archaeometry, that vast, quiet plane where chemistry, physics, archaeology, and history unite. According to current archaeological data, obsidian trade dates back at least 14,000 years to the Upper Paleolithic period. This history is observed independently in geographically completely separate regions from each other, such as the Middle East, Anatolia, the Aegean region, Central America, the Andes Mountains, Southeast Asia, and Melanesia. What does this independence mean? It means that people in different geographies, unaware of each other, discovered the same potential on the same material. Obsidian told everyone the same thing. This language was universal. But how do they trace this trade? How is it known that a piece of obsidian broken from a volcano in the east of Anatolia is in a tool found on the island of Cyprus? The answer is in light, in physics, in spectroscopy. The obsidian of every volcano is chemically different. According to current geochemistry data, depending on the source of the magma, in which tectonic environment, from which mantle region, together with which crustal material it was melted, the ratio of trace elements inside it changes. Strontium, barium, zircon, rubidium, scandium, lanthanides. The amount of each of these is different. These differences are almost like a fingerprint. Obsidian, coming from a volcano in the Cappadocia region of Turkey, differs spectroscopically from obsidian coming from the Lipari island of Italy. These differences are not visible to the eye, but they are read with devices. This technique, named X-ray fluorescence spectroscopy, or neutron activation analysis, is carried out by various methods. Archaeologists take an obsidian artifact found in a site, conduct its chemical analysis, then compare this signature with the database of known volcanic sources. As a result, an address is obtained. This piece came from such and such mountain, and this mountain is this far from this archaeological site. This distance is sometimes 100 kilometers. Sometimes it is 500. sometimes 1,000 or 2,000 kilometers. The Anatolian obsidian trade presents one of the most beautiful examples of these researches. According to current archaeological data, Anatolia had two main obsidian sources: the Çiftlik Acıgöl site in the Cappadocia region and the surroundings of Mount Nemrut near Lake Van. Obsidian coming from these two sources spread over a wide geography of the Middle East, from the Levantine coasts to Mesopotamia to Cyprus, even to Egypt. This spread map is a map of human movement, trade, connection. Of course, this trade was not an organized enterprise, at least in the early periods. Current archaeological models suggest that this spread mainly occurred through down-the-line exchange. That is, obsidian passes from hand to hand. A short distance is covered in each exchange, but as a result of many exchanges, it reaches long distances. From one human community to another, from one generation to another. This process could continue for centuries, even millennia. Stay with this idea for a moment. A piece of obsidian, without any human carrying it to its final destination, has traveled thousands of kilometers by passing from the hands of humanity to hands. Every person who held it lived their life, died, was forgotten, but the obsidian remained in the next hands. Çatalhöyük is one of the most beautiful archaeological windows of this history. According to current archaeological excavation data, Çatalhöyük, this Neolithic settlement in the south of Anatolia, inhabited approximately between 7,500 and 5,700 BC, is a place where the use of obsidian was massive. Among the obsidian artifacts found here are arrowheads, knives, scrapers, even waste flakes created during sharpening, debitage. These flakes are particularly interesting because they show that obsidian was worked there. The material was not only brought as a finished tool, people shaped it there themselves. Obsidian working, this process called knapping, was a craftsmanship. It was necessary to strike the correct point on the stone at the correct angle. An excessively strong strike crushed the stone, while a very weak strike did nothing. Learning this craft required years. Modern experiments, current experimental archaeology studies, show that to make a high-quality obsidian tool, both deep knowledge about the material and motor skill acquired over a very long period of time are needed. Think about this craft for a moment. A person, perhaps 10,000 years ago, holds the piece of obsidian in his hand up to the light. He reads the edges of the piece, the lines inside it, the weak points of its structure. His fingers feel the coldness of the material, its smooth surface, that its edges are sharp. Then he holds the stone with a protection made of clothing leather, strikes the correct point with another stone or bone. A long, smooth blade, sharp on both sides, blade breaks off and separates. This blade is already a tool. Perhaps that person did not consider this moment great for himself, making tools, hunting, resting. Perhaps this was a part of his daily life. But that piece of obsidian has remained frozen in that moment ever since. In a museum, or from a box inside an archaeological excavation, like a piece taken out to the street 100 years ago, it is within the flowing of time over it. The last human hands that touched the surface of this piece were perhaps 10,000 years ago. And tonight, through this text, that piece was talked about a little. The Mesoamerican obsidian trade, however, is a completely different story. According to current archaeological data, obsidian sources in Central America, especially sources around Teotihuacan in central Mexico, sites like El Chayal, Ixtepeque in Guatemala, were a material of both trade product and political significance for the ancient civilizations of this region. It is thought that a part of the power maintained by the city of Teotihuacan from the 1st millennium BC to the 7th century AD was related to the control over the obsidian trade, but archaeological debates continue on this subject as well. What is interesting is this. In Anatolia, in Mesoamerica, and in Melanesia, we see that obsidian trade routes follow the same basic dynamics: large production close to the source, then spreading to long distances with gradually decreasing quantity. This model is archaeologically called fall-off curve, fall curve. As one moves away from the source, the amount of obsidian found decreases. It is possible to understand the trade model by how this drop occurs. There is something worth thinking about within this movement. Obsidian carries its origin. No matter how far it goes, how many hands it changes, how much time passes, the chemical signature inside it remains. There is no way to change those trace element ratios. It cannot be erased. It cannot be covered up. We do not know which hands it passed through, but we know where it came from. Tonight, your body also has its own chemical signature. The isotope ratios inside your cells, strontium isotopes, for example, keep traces of your childhood food, the water you drank, the soil you grew up in. So much so that forensic archaeological researches using these isotope signatures can determine the origin of ancient human remains, in which geography they grew up. You too carry a source. Your own story is inside it. But tonight, there is no need to read that story. Just knowing is enough. It is also necessary to talk briefly about obsidian hydration dating, because this process itself is a slow, quiet process, like a dream. When an obsidian surface is exposed to air, water molecules slowly diffuse from the inside towards the outer surface. This process is geologically called hydration. When a piece of obsidian is broken, chipped, that is, when a surface emerges, hydration starts from zero. And the thickness of the hydration layer on this new surface increases over time. According to current scientific models, measuring this thickness, knowing the hydration rate, which depends on temperature, allows estimating when the artifact was used, that is, when the surface was opened. This technique is not perfect. The hydration rate depends on factors such as the temperature, humidity, chemical environment of the soil. But when used together with other dating methods, it provides valuable information. So obsidian marks every touch on itself, every new surface with time. The diffusion of water continues for hundreds of years, thousands of years. This slow process works like a clock, but the hand of the clock is not visible to the eye. It is only read with a microscope, with light, with measurement. Time always leaves a trace. Throughout the night, biological processes in your body continue. The firing rate of neurons changes, heartbeats change, the body regulates heat loss. These processes proceed automatically and naturally. Obsidian has already cooled. The heat inside the magma is gone, but the positions of the atoms remain in an amorphous structure. The speed of cooling has determined this irregular yet stable structure. Sometimes the oldest material holds the answer to the most modern question. This thought seems hasty, but it settles when you think about it slowly. Obsidian has been in human hands for 14,000 years, yet the questions about it have not ended. On the contrary, new fields of science are looking at this ancient volcanic glass again on a smaller scale, with deeper questions at the nanoscale, at the molecular level, with surgical precision. Tonight, without rushing, one by one, we are inside that new perspective. The connection of obsidian with surgery is one of the most interesting intersection points of modern science. According to existing medical research, when steel surgical scalpels are viewed under an electron microscope, a series of small teeth, microscopic notches, are observed on their edges. It is accepted that these teeth originate from the crystal structure of the scalpel's metal. Metal atoms are arranged in a crystal lattice. The edge of this lattice cannot always be perfectly smooth. In terms of dimensions, the edge thickness of a steel scalpel is around a few hundred nanometers. Obsidian, on the other hand, has an amorphous structure. There is no crystal lattice. This means that when it breaks, the edge is cleaved atom by atom. It is not dependent on the arrangement of the crystal lattice. Theoretically, an obsidian edge can be sub-nanometer, that is, a few atoms thick. Some studies discuss that this edge precision is comparable to steel scalpels in certain contexts, but this comparison depends on many factors: which type of obsidian, how it was broken, to which tissue it was applied. It is not scientifically correct to make a definitive claim of superiority. Nevertheless, some surgeons, especially some researchers in the field of microsurgery, have made experimental incisions with obsidian blades and observed the trace of those incisions in certain tissue types. These experiments do not always translate into clinical application. There are practical difficulties such as sterilization, durability, and standardization, but the scientific interest continues. This interest itself shows one thing: the ancient material has not fully unlocked its potential. It still has questions inside it. The amorphous structure of obsidian is also interesting from the perspective of nanomaterials science. Based on existing material science research, amorphous materials, glass as well as various amorphous metals, amorphous semiconductors, can show superior properties to their crystalline counterparts in some areas. Amorphous metal coatings, for example, sometimes provide a smoother, more homogeneous surface because crystal grain boundaries do not exist. These boundaries sometimes create a point of mechanical weakness. In an amorphous structure, these weak points do not exist, but instead, other properties change. Obsidian is a natural model system in this regard. Billions of years ago, the Earth itself created an amorphous silicon dioxide structure under special conditions. In modern laboratories, synthetic amorphous silicon dioxide, that is, glass, is produced for various technological applications: optical fibers, microelectronics, the semiconductor industry. However, obsidian, which the Earth created in its own laboratory, is still a not fully understood model. For a moment, without rushing, think of the nanometer scale. 1 nanometer is 1/1000th of a meter. The width of a strand of hair is approximately 80,000 to 100,000 nanometers. So the nanometer scale is 100,000 times smaller than a hair strand. At this scale, the rules of physics behave a little differently. Quantum effects, electron tunneling, the discretization of energy levels become significant at this scale. When the edge structure of obsidian is viewed at the nanometer scale, we see an irregular but continuous structure of the amorphous silicon dioxide network. Tetrahedra are connected to each other. Each silicon is bonded with 4 oxygens, but the lengths and angles of these bonds differ slightly from one another. In crystalline quartz, these bonds are completely regular. Every silicon-oxygen bond is the exact same length. In obsidian, however, these lengths show a statistical distribution like a Gaussian curve. There is an average, but every atom has slightly deviated from that average. This deviation, this irregularity, is what makes obsidian what it is. The smoothness at its edge, its relationship with light, comes from this irregularity. All the unique features of the amorphous structure are inside this irregularity. Irregularity is sometimes the condition of perfection. Tonight, your body is also not completely symmetrical. Your left hand is slightly different from your right hand. One side of your face differs slightly from the other. The protein folding inside the cells, the 3-dimensional structure of proteins, is not perfect, but it is functional. Biological systems have adapted not to perfect order, but to functional order. Complete symmetry rarely provides an adaptive advantage in the biological world. Obsidian is like this too. It lacks a complete crystal order, but this is not a deficiency. This is its characteristic and its strength. Let's look a little further into modern science, this time from the perspective of spectroscopy. According to existing analytical chemistry research, obsidian gives a very characteristic signature in X-ray fluorescence spectroscopy, XRF. In this technique, high-energy X-rays are directed onto the material. The atoms inside the material absorb this energy, then emit energy at their own specific wavelengths. Each element has its own fingerprint, its unique emission spectrum. As a result, the elements within the material can be identified both qualitatively and quantitatively. For obsidian, this analysis is applied in several fields. The first field we already mentioned, provenance determination. But the second field is a more modern application, the evaluation of obsidian coatings. In some industrial research, amorphous silicon dioxide coatings, materials chemically similar to obsidian, are investigated in terms of properties such as corrosion resistance, friction reduction, and biocompatibility. Although obsidian is not directly applied in this field, its analysis is used as a model system. And the third field is more unexpected. This is geothermal energy. According to existing geothermal energy research, volcanic zones that are a source of obsidian are, at the same time, areas where underground heat sources are close. Iceland is the clearest example of this connection. Iceland is both an active, volcanically active island and a country that widely uses geothermal energy. Underground heat turns into water vapor, This vapor spins turbines and electricity is produced. A large part of Iceland's electrical energy is provided in this way. Obsidian is not a direct part of this process. However, it is a product of that geological environment. In regions with high geothermal potential, obsidian sources are also often nearby because both are the result of the same volcanic activity. Obsidian acts as a marker. Its presence indicates the existence of intensive volcanic activity in that area. Tonight, that heat is beneath the earth. Even at this moment, kilometers below from where you are sitting or lying down, under the cooled crust, it exists in a slow, quiet, but present state. Another modern intersection point, obsidian and paleoclimatology. According to existing paleoclimatology research, obsidian-sourced volcanic eruptions emit massive amounts of aerosols into the atmosphere, especially sulfur dioxide. When these aerosols reach the stratosphere, they partially reflect solar radiation. As a result, temporary global cooling can occur. In history, the traces of this effect have been preserved in ice core drillings. The chemical signatures within the ice layers retain the characteristics of past volcanic events. What is interesting is this. Obsidian itself plays an indirect role in these paleoclimate reconstructions. Dating the obsidian source, determining which volcanic event occurred and when combined with climatological data, helps to understand past climate changes. The chemistry of an obsidian piece, its date of formation, the power of the eruption, when these are read together, a mosaic of the past emerges. When looking at science, we often see one thing: everything is connected to everything. Obsidian is connected to surgery through its sharpness. It is connected to nanomaterials through its amorphous structure. It is connected to geothermal energy through its volcanic origin. It is connected to paleoclimatology through the history of its origin, connected to archaeology through human history, connected to optics through its relationship with light. These connections spread like a web. You start from one point, obsidian, and you soon see that this point is tied with a thread to almost every field of science: material science, analytical chemistry, geophysics, archaeometry, medicine, energy. Every connection within this web is a field of research. Every field of research is a lifetime. Every lifetime means thousands of questions. But tonight, none of these questions need to be answered. You are simply inside this web, like obsidian frozen in a moment of time, yet you are at a point connected to everything. I want to touch upon one more modern application, this time returning to optics. According to existing optical engineering research, amorphous silicon dioxide, the main component of obsidian, is used as the primary material in the production of optical fibers. Optical fibers are thin glass strand structures that carry light over long distances. Most of the internet passes through these fibers. Data flows like photons, like light, through silicon dioxide. A message you sent today, or this video itself, while reaching from one point to another, has perhaps passed through optical fibers many times. The silicon dioxide inside that optical fiber is chemically a sibling to obsidian. The same basic structure, the network of SiO4 tetrahedrons, is inside both of them. One emerged from the volcanic oven of the Earth. The other forms the basis of humanity's information infrastructure. From the volcano to optical fibers, the structural similarity directly connects us between the ancient material and modern technology. Tonight, when you close your eyes, or if they are already closed, listen to your breath for a moment. The oxygen in every breath, as we just said, carries a story. But the breath itself is also a physical phenomenon. The diaphragm muscle pulls down, the chest cavity expands, and as a result of the pressure difference, air flows in. This process is controlled by the autonomic nervous system. You don't command it, it just works, like Obsidian. The physics inside it works. You don't control it. Chemical bonds exist. Electron clouds spin around the atoms. The network of SiO4 tetrahedrons is in its place. No one commands it, but it exists. It is continuous. It is calm. You are like this right now, too. Continuous, calm, present. The earth is not alone. We say this sentence in an astronomical sense, but to say it in a more concrete way tonight, the volcanic process, turning into glass, the amorphous silicon dioxide structure, these do not belong only to this planet. Various bodies of the solar system preserve their own volcanic histories, their own glass structures, their own cooling points. Space works like a vast laboratory. Every planet, every moon, every asteroid experiences the same physics under different conditions, with different elements, at different speeds. Tonight, without rushing, we want to look at that vast laboratory from one planet to another, slowly. Let's start with the moon. Based on current lunar geology, or selenology in scientific language, data, the surface of the moon is largely covered with a fine-grained blanket called regolith. This regolith is the result of meteorite bombardment over billions of years. Small and large bodies struck the moon's surface, shattered the rocks, melted them, and then that melted material rapidly cooled. This cooling process often creates glass particles, lunar glass. It is white transparent, sometimes tending towards orange, sometimes dark. But is there volcanic glass like obsidian on the moon? According to current lunar sample analyses, including rock samples collected during the Apollo missions, some glassy rocks originating from the moon's basaltic lava flows have been encountered. Especially the so-called pyroclastic particles thrown into the air during a volcanic explosion cause the orange-red soil color on some regions of the moon. When astronaut Harrison Schmitt discovered this orange soil during the Apollo 17 mission, this was the first direct example showing the presence of volcanic glass particles. The moon's volcanism was active billions of years ago. According to current radioisotope dating data, the most intensive volcanic activity was approximately 4 to 3 billion years ago. Since then, the moon has slowly cooled. The heat inside it has decreased. Its surface has frozen. A frozen planet. The heat inside it has long gone, but the traces of that process, those glass particles, that orange soil, are still there. Let's move to Mars. According to current Mars geology research, Mars also has an intensive volcanic past. Mount Olympus, Olympus Mons, is the largest known volcano in the solar system. Its height is approximately 21 to 22 kilometers, 3 times higher than Everest. Its width is more than 600 kilometers, almost equal to the territory of France. This giant volcano is the result of a hotspot on Mars remaining active in the same place for billions of years. Because tectonic plates move on Earth, volcanoes over a hotspot cannot become huge. The plate moves and shifts away from the source. Because plate movement on Mars is much slower, or practically non-existent, heat has flowed to the same point for millennia, for millions of years. Mount Olympus is the result of this process. But is Mars currently volcanically active? Current Mars research does not yet fully answer this question. The Mars seismometer of the InSight probe has recorded seismic activity on Mars. It is discussed that a part of this activity could still be related to active geological processes. But research on this topic is still ongoing. A definitive conclusion is not possible according to current data. The presence of glass components has been identified in basaltic rocks on Mars. Glassy material within meteorites that have fallen to Earth and been confirmed to be of Martian origin confirms this connection. That glass holds traces of Mars's volcanic past. Io, one of Jupiter's moons, is a completely different story. According to current planetary geology data, Io is the most volcanically active body in the solar system. Jupiter's immense gravity constantly squeezes, stretches, and heats Io. This process is called tidal heating. As a result, Io's interior is always in a molten state. Its surface is constantly changing. New lava flows, new craters, new glassy coatings. Glassy structures on Io change rapidly, some within hours. A new lava flow covers the old glass, cools itself, and turns back into glass again. This process continues uninterrupted. Obsidian on Io, if it can be called that, might be a material that lasts within hours. The comparison with obsidian is thought-provoking. Obsidian on Earth remains for millions of years. Its amorphous structure protects it. But the glassy material on Io changes quickly because volcanic activity is unceasing. The same physics, a completely different timescale. Venus also adds its piece to this mosaic. According to current Venus geology data, largely based on radar mapping data from the Magellan spacecraft, the surface of Venus is covered with vast volcanic plains, lava flow channels, and various volcanic forms. Determining whether Venus's volcanic activity currently continues has been difficult from Earth, but research in recent years has begun to discuss some signs. According to what current scientific models suggest, the surface of Venus may retain traces of relatively recent volcanic processes, but this topic is still an active research subject. Venus's extremely dense atmosphere, mainly consisting of carbon dioxide, 90 atmospheres of pressure at the surface, 465 degrees Celsius average temperature, makes it difficult for glassy materials to remain there for a long time. But the rules of physics are the same. If magma cools rapidly, glass is formed. Although rapid cooling conditions on Venus are not low, the temperature is slightly lower in certain high-altitude regions. There, various chemical processes occur differently. According to current meteoritics research, certain meteorite groups, especially the types called impactites, preserve glass structures. Impactites are the result of large meteorite impacts. During the impact, local rocks melt instantly, then cool rapidly, eventually turning into glass. The Libyan desert glass in the Libyan desert is the most famous example of this type. According to current research, this glass is the result of a massive impact or an atmospheric explosion event that occurred millions of years ago under the Sahara. Chemical analyses show that this glass was formed at a very high temperature. Earth's rocks experience such a temperature only in massive cosmic impacts. It is suggested that a blade made from Libyan desert glass was found among Tutankhamun's burial artifacts. This claim was widespread for a while. However, current archaeological and chemical analysis data show that this connection is more nuanced. The discussion still continues. Regardless, it is known that ancient Egypt valued this glass. Perhaps they sensed its story, a substance fallen from the sky, or perhaps just its beauty. Tektites are another category entirely. According to current tektite research, tektites are glass bodies formed as a result of melted earth rock thrown into the air during massive meteorite impacts, flying long distances and cooling. They are usually small, dark-colored, and aerodynamic in shape because they took their form while flying through the air. The surface of some is covered with small pits, ablation, or wear marks, a part of the surface vaporized while passing through the atmosphere. Tektites are found in several broad regions. The Australasian tektite strewn field covers Asia and Australia. The Bohemian tektite field is in Central Europe. The Ivory Coast tektite field is in West Africa. Each field corresponds to a specific impact event. A tektite is thought-provoking. It was created from Earth's material but thrown outward into the atmosphere, formed there, and then returned. Detached from the Earth, flew in the air, and returned to the Earth again, a kind of cosmic journey, but only within the atmosphere. One thing emerges from all this planetary comparison. Glass, the amorphous structure, emerges in different bodies of the solar system under different conditions at different times. The law is the same: rapid cooling, no time left for crystallization, the amorphous structure is formed. This law works in the volcano of the Earth, in the microglass in the Moon's regolith, in the glassy material in Mars's meteorite sample, and at the moment of a cosmic impact. According to current understanding of physics, this is not a coincidence. Silicon dioxide, a widespread compound in this universe, always creates an amorphous structure under certain rapid cooling conditions. This feature is inherent to the material itself. Like a mathematical truth, it works regardless of the environment, regardless of the planet, regardless of the time period. Tonight, think of a piece of obsidian. That piece is the product of a volcano, but that volcano is, at the same time, the surface manifestation of the Earth's internal heating system. This thermal energy stems from energy gathered during the planet's formation stage and preserved until today, partly as a result of the decay of radioactive elements. This connection, extending from a piece of obsidian to the deep layers of the planet, is explained within the framework of modern geophysical models. Every stage is substantiated by observations and measurements. Yet the scale of this chain, the aesthetic completeness of this sequence, carries a depth that no measurement can fully express. Just as in water droplets in a rainbow, the refraction of light happens everywhere and at every moment. Photons continuously encounter materials. Their effective speed decreases within the medium, their direction changes, and sometimes they are absorbed. Electrons in atoms reside at certain energy levels. The magma beneath the Earth moves slowly. The regolith on the surface of Mars expands slightly in the cold night and shrinks again in the daytime heat. A new lava flow on the surface of Io cools rapidly and vitrifies. All of this happens at this moment, everywhere, at the same time. And you, in this moment, in this calm, slow, rested moment, are a part of this universe. You are not a piece broken off from the Earth. You are upon it. And the Earth is a part of the solar system. The solar system is in an arm of the Milky Way galaxy, and the Milky Way is among billions of galaxies. This scale does not fit into the mind, this is true, but not fitting does not make it any less real. Tonight, you too can think of your existence not as an answer, but as determined yet not fully explained, incomplete yet whole, as an open question. Think of a glassy material belonging to another body of the solar system. For example, think of a small glass particle in a meteorite of Martian origin. Inside which star were the silicon atoms in its composition formed? Which supernova explosion scattered them into space? Which cosmic dust cloud brought those atoms together, subsequently creating the conditions for them to turn into a planet's rock? With current data, it is not possible to give an exact answer to each of these questions, but the question itself is a silent, open, and ongoing part of the scientific perspective. Tonight, you too can think of your existence not as an answer, but as determined yet not fully explained, incomplete yet whole, as an open question. To understand the properties of obsidian, one can physically observe it. Scientific explanation is one thing: atoms, molecules, refractive indices, amorphous structures. When touching obsidian, a person immediately feels its physical properties. This sensation is scientifically explained by heat and touch receptors. That reaction comes even before the fingers feel the surface. The skin registers the coldness. The eye looks into the dark depth. Tonight, we are within those senses. No numbers, touch, sound, light, weight. Slowly, one by one. First, let's talk about touch. Initially, we can say that obsidian is cold. When you take it in your hand or imagine it, that coldness under the fingers is immediately felt. Why is this coldness like this? Because obsidian, like all stones, is different from the skin in terms of thermal conductivity. According to existing thermal physics data, when a material touches the skin, two things can happen. Either that material takes heat from the skin, it feels cold, or it gives heat to the skin, it feels hot. Because obsidian is a material with relatively high thermal conductivity, it rapidly draws the skin's heat to itself. The fingers feel this energy transfer process as coldness. This coldness is temporary. After a few seconds, the obsidian warms up under the fingers. It has taken the heat of the skin. It is no longer cold, nor is it hot. We can say it is neutral. It has reached body temperature. This transition, coming to a neutral state from that initial coldness, is a very slow process. It is as if obsidian accepts. Slowly, it takes the heat inside. Next, let's talk about smoothness. The surface of obsidian is smooth, but this smoothness is different from the smoothness of glass. Ordinary window glass is slippery, sometimes holds fingerprints, sometimes makes you feel a slight stickiness. Obsidian, however, has a drier smoothness. Its surface responds to touch but does not grip. The finger glides over it, but it is not slippery. This difference is hard to explain, but nevertheless, the hand feels it. Behind this, there is again that amorphous structure. The surface of obsidian, on a microscopic scale, has very little roughness. The edges of crystal minerals are formed according to the cutting angles of the crystal lattice. Sometimes small steps, small protrusions occur. The amorphous structure of obsidian, however, does not allow for these steps. The fracture is conchoidal, arc-shaped. As a result, the created surface is in the form of microscopic waves, but these waves do not create roughness on a scale that the finger would feel. The finger only feels smoothness. Think of your fingers for a moment. The skin layer at the tips of your fingers, that thin epidermal layer under the dermis, is full of touch receptors. Meissner's corpuscles respond to light touch. Pacinian corpuscles respond to deeper pressure, vibration. Merkel discs register details of shape and texture. These receptors send signals from nerve fibers to the brain's somatosensory cortex. There, they are processed like a map. A hand holding obsidian activates all of these receptors. The coldness comes from thermoreceptors. Smoothness is registered via Merkel discs, and weight is registered by deep touch receptors. The brain processes all these signals at once. The result? Obsidian. Cold, smooth, heavy, real. Tonight, think of your fingers or your hands. Where are they now? On the bed? On your stomach? Just feel. What do they feel? The texture of the fabric, the softness of the blanket, the coldness of the air. These receptors are working. Give them a little attention tonight. Now, sound. Obsidian makes a sound, but only at certain moments. When you tap one piece against another, the resulting sound is characteristic, high frequency, short, glass-like, but fuller. The physics of this sound is also interesting. When two solid objects touch, waves propagate in both materials, reflect on the surface, create interference, and as a result, the heard sound is shaped according to the elastic modulus, density, and shape of those materials. The elastic modulus of obsidian, that is, its resistance to deformation, is comparable to ordinary glass, but slightly higher. This means that obsidian transmits vibrations relatively quickly. As a result, the sound is high and clear. However, when obsidian breaks, or when a strong blow strikes it, the sound is completely different, shorter, sharper. The energy spreads instantly, sometimes a cracking, sometimes a small snapping. This sound comes like a warning. The energy inside the stone has been suddenly released. Tonight, however, there is no blow, there is no cracking, it is silence. Listen to the silence. Think of the quietest moment in your room tonight. Silence is never complete. There is always something, the settling of the building, the sound of a distant car, the beating of the heart. Maybe your ears feel it, the rhythm of the breath. These are background sounds. The mind does not usually pay attention to them, but now do it slowly. The silence inside obsidian is deeper. For millions of years, under the earth or in a cavity within a rock, it has heard no sound. Vibrations, seismic waves of earth tremors, the distant pressure of ocean water, meteorological events have passed through it with infrasound. But obsidian has not heard them. Metaphorically speaking, it has felt them. As a solid material, it has passed these waves through itself, but as a passive listener, it has given no answer. Tonight, you are also a passive listener. There is no need to answer anything, just feeling is enough. Now, let's talk about smell. Obsidian itself is almost odorless. This is due to its smooth, non-porous surface. Odor molecules, volatile organic compounds, stick to the surface of the substance, then spread into the air, reaching the nasal receptors. Porous materials, wood, earth, clay, retain more smell because they have extensive internal surfaces. Obsidian, however, is low in porosity. Its surface and the smell it holds are minimal. But newly broken obsidian is different. Amorphous silicon dioxide can contain a very small amount of volatile compounds trapped in its density. During breaking, these are released. Some people have stated that newly broken obsidian has a very faint, characteristic smell, that stone smell, typical of siliceous minerals. This smell is very faint, very brief, but it exists. The smell of a newly broken stone is different from the earth rain smell called petrichor, but it is something related to it. Both are the smell of the moment minerals open up to the atmosphere. Tonight, close your eyes, or if they are already closed, continue. For a moment, think only of smells. The smell in your room, the smell of the blanket, maybe the smell of rain, or the smell of the night's cold air. These are chemical signals. Molecules bind to receptor proteins in the nasal epithelium, turn into electrochemical signals, and go to the brain's olfactory cortex. From there are close passages to the emotional centers, the amygdala, the hippocampus. This anatomical proximity explains why smell can trigger strong emotional memories. The cold, low-odor surface of obsidian, however, does not start this sequence of memories. It remains neutral. It does not interfere. It is just there. And now, color. Obsidian is not black, not completely black. If you look at it in daylight, especially under a strong light source, its surface shines faintly. This shine is not heat reflection, it is specular reflection. That is, it is the smooth, amorphous surface reflecting back the light coming at a certain angle. It is mirror-like, but not perfect. If the light angle is right, the color inside this shine sometimes becomes visible. A purple tint, sometimes dark green, sometimes different tints in different regions of the surface, because the amorphous structure inside obsidian is not completely homogeneous. Localized iron accumulations, localized magnetite particles, localized different densities, these slightly change the angle of light reflection. The result, a shining black obsidian with depth, an obsidian that is never flat and never ordinary. Think of the type called rainbow obsidian. According to existing mineralogy research, the iridescence effect in this rare type of obsidian stems from the alignment of microscopic magnetite crystals within the obsidian. These crystals are aligned in parallel in very thin layers, sometimes only a few hundred nanometers thick. When light passes through these layers, interference occurs. Different wavelengths strengthen or weaken at different angles. As a result, when the eye moves, the color of the surface changes, from yellow to orange, from green to blue, changing according to the position. This effect is the same mechanism as the colors in a soap bubble and the colors in an oil slick on water. Thin layers, interference, color. This mechanism is universal, But this effect in rainbow obsidian has been inside it for hundreds of thousands, maybe millions of years. A soap bubble is seconds, an oil slick is minutes. Rainbow obsidian, however, is on a geological timescale. The beating of the heart. Steady, rhythmic. It starts from a point, spreads like waves along the veins. The rhythm of the breath. Inhale, pause, exhale, pause. These pauses, these little moments of silence, are the moments when the diaphragm relaxes, the lungs contract with their own elasticity, the air comes out from inside. Then this process starts again. The electrical signals inside the nerves are more irregular, but calmer tonight. Neurons firing all day gradually calm down. Synaptic activity decreases. The brain starts its own garbage collection. Metabolic waste collected during the day mixes with the cerebrospinal fluid, filtering from the inside out. This process, tonight's cleansing called the glymphatic system, is fully active only during deep sleep. That is, tonight the brain cleans itself. There is no need for you to do anything to help this. This time, let's return more slowly to the coldness of obsidian. Think of the piece of obsidian in the palm of your hand. It has weight. A small piece may be 100 grams, but this weight is felt when holding it. The weight draws your consciousness to a single point, into your hand. The mind gathers at that point. Thoughts from throughout the day, work, plans, worries are pulled aside for a moment. There is just it, the weight, that coldness, the touch of that smooth surface. This is not any kind of meditation or behavioral advice. It is simply possible to feel its heat, smoothness, and weight while holding obsidian as a physical sensation. Why? Because perhaps physical sensation is always in the present. It is not past or future. This moment, this touch, this coldness. The physical state of obsidian is stable. Its chemical and structural properties are always the same and do not change over time. For it, only this moment exists. This dryness held by chemical bonds. Every moment of this surface where photons are absorbed. This touch where heat flow continues, exists. Tonight, you too return to this moment. And the final sense, sight. Obsidian is black in color, and its surface absorbs light. In some parts, however, different tints can be seen due to the reflection of light. The blackness of obsidian is a color that absorbs light, but that blackness has its own depth. If there is light at the edge of the piece, that light filters inside, spreads there, doesn't go very far, but it goes a little. You cannot see where that light goes, but you know that it goes. Tonight, the eyes slowly become heavy. That heaviness is the arrival of sleep. It is a physiological process. Adenosine, a neuromodulator accumulated as a result of activity inside the brain throughout the day, strengthens sleep signals when it reaches a certain threshold. This chemical process is not outside a person's will. It occurs within oneself. It is not started consciously, but when the time comes, it appears. When the eyes close, vision is not completely cut off. It simply turns inward. The mind begins to create its own images in a slow, free, illogical, yet orderly form. Everything returns to one place. A long journey was made tonight. It started from the depths of the volcano, advanced towards the physics of light, passed through the touch of human hands, wandered among the planets, and peeled back the layers of emotions. And now the movement changes its direction, not towards the beginning, towards the end. But every end is the threshold of another beginning. It is always like this. Obsidian silently reminds us of this. Time also flows this way. At this moment, the body is calm. The breath has found its rhythm. The mind follows the words, not tightly, but with a light connection. This connection is not tense like a rope. It is more like a distant light. Its presence is felt, but it cannot be caught. And the transition from one stage to another sometimes looks exactly like this. Let's think about the life of Obsidian once, from the very beginning. Millions of years ago, according to current radioisotope dating data, some obsidian deposits date back to periods older than 10 million years. The heat inside the Earth gathered at one point. Convection currents in the mantle, those slow, heavy, invisible movements, pushed the rocks upwards. Silicon-rich magma rose upwards. It found a crack somewhere. It began to flow. Then it cooled. Within seconds or a few hours, the surface of the flowing material froze. The network of silicon-oxygen tetrahedrons solidified in an irregular manner. A crystal lattice did not form because there was no time. Every atom kept its place within that moment of flow. It froze and remained. From that moment to this night, that piece of obsidian exists. Let's slowly consider what this existence means. What does a piece of obsidian experience during the years it lies underground? In a geological sense, it experiences very little. Chemical bonds are preserved, hydration slowly continues, water molecules diffuse to its surface, a layer is formed. This layer remains 1/1,000,000th of a millimeter thick, but it continues there. Earthquakes come and go. Seismic waves pass through the material, but do not change it. Life on the surface of the earth, its roots, insects, soil microorganisms lives around it, but obsidian itself is calm. It does not change. This is a stability, but not a lifeless stability. It is a chemically active storage. Every atom inside it keeps its electron cloud. Every bond stores energy. This energy is in the form of heat, but at a very low temperature, in a very quiet way. Obsidian rests, but it is in an active rest. The body is in a different rhythm tonight. It is in a state of active rest. During sleep, the body continues various biological processes. For example, cell repair and the alteration of hormone levels. Repair mechanisms are activated in cells. Damaged proteins are renewed, and regeneration processes are accelerated in some tissues. The activity of the immune system changes according to the circadian rhythm. and growth hormone is secreted at its highest level during the deep sleep phase. The body continues various biological processes during sleep. This stage, which looks calm from the outside, is full of coordinated biological activity on the inside. No conscious effort is required. The process continues on its own course. Think of an archaeological moment, the moment Obsidian is unearthed. An archaeologist, or simply a human 1,000 years ago, saw something in the dirt, a shining edge. That small gleam caught by a black surface from the light filtering through the soil. They bent down. Their fingers gently pushed the soil aside. The piece emerged. This moment of unearthing is a physical change for the matter. The material that has remained under constant temperature and pressure for millions of years comes out into the open air again. It comes into contact with oxygen. It faces a temperature difference. From a scientific perspective, there is no experience here. The material does not feel, does not observe. But the idea of coming into the light after a long silence holds a special place in human consciousness. Sometimes what changes is not the matter, but the gaze that sees it. Where will Obsidian go tonight? Tonight, it exists as a thought. It is within a conversation. Tomorrow, however, it might be in another context, behind a museum display case, on the page of an archaeological catalog, still unrevealed beneath the earth, or on a collector's shelf. According to existing archaeological data, many obsidian sources in the world have not yet been fully documented. Every year, new deposits are identified, new artifacts are found, and ancient trade routes are mapped more accurately. Knowledge about this material is continuously expanding. The world is not fully mapped. There are still unexplored layers beneath the earth. Unanswered questions exist. Some stories are only known in fragments. Not all answers emerge immediately. Some will never be complete. Tonight, somewhere on Earth, there is most likely a piece of obsidian under a layer of soil, untouched by human hands, having seen no light 100 meters deep. What is that piece doing right now? From a physical point of view, it maintains its metastable amorphous structure. Its atoms are in a state of thermal motion. Its chemical bonds remain stable. Unless the temperature and pressure change, no noticeable change occurs in its structure. This condition can continue for millions of years. For matter, this is not a special event. It is simply a state of existence. On a geological timescale, the difference between doing and being almost disappears. It is doing what it has been doing for millions of years, preserving its existence. Let us look at human history one last time. According to existing anthropological research, obsidian was shaped by human hands from the Paleolithic to the Neolithic period, and from there to the Bronze Age. Then came metal, first copper, then bronze, then iron. Metal replaced obsidian, more durable, easier to shape, more widespread. Obsidian was put aside as a tool, but it did not go away. It continued to be used for decorative purposes, as jewelry, as an ornamental object, as a mirror. In later centuries, science began to study it. Chemical analyses, dating methods, research in the medical field. And today it is inside museums, behind glass displays, under light, next to explanatory plaques. But it is also beneath the Earth, still undiscovered. It is also in researchers' laboratories, still not fully understood. It is also within this conversation tonight. Let us take one last look at the geology of the Earth on a grand scale this time. According to existing geological timescales, the Earth formed approximately 4.54 billion years ago. The early stage, the Hadean Eon, covers the first hundreds of millions of years of planetary history. During this period, most of the surface was under high temperature conditions. Intense meteorite impacts occurred, and the atmosphere was completely different from its current composition. Direct rock samples from that period are almost completely unpreserved because subsequent geological processes remelted, transformed, and altered the materials. But zircon crystals carry information about the early Earth. According to radiometric dating, some zircon samples found in Australia show an age of about 4.4 billion years. This figure points to a period very close to the beginning of the planet's history. Obsidian is not that ancient. Geologically, it is a relatively young volcanic glass, but it is also the result of this planet's internal heat system, the product of convection processes occurring in the mantle, the rise of magma, and rapid cooling. This internal energy mechanism has been operating for billions of years. Every volcanic eruption is the visible expression of that energy on the surface. The surface of the planet might seem calm, but beneath it, a continuous thermal and mechanical dynamic exists. At this moment of tonight, the state of the mind changes. Thoughts are still emerging, but slower, more freely. One thought arises, stays for a short time, then is replaced by another. The logical connection between them may not be as tight as it is during the day. This stage is called hypnagogia, the transitional state between wakefulness and sleep. During this time, images can be more visual, more non-linear. Sometimes they seem beyond logic, but usually they are not disturbing. Obsidian is also formed as a result of a transition. The rapid cooling of magma does not allow a crystal structure to form. As a result, atoms do not establish long-range order, and an amorphous structure is formed. This is not a stable staying in between, but a rapid kinetic cessation. The transition to sleep is similarly a gradual transformation. Wakefulness does not disappear suddenly. The structure changes gradually. Transition moments are often short, but it is precisely these intermediate stages that show the change itself. After a while, the first stage of sleep begins. According to modern sleep physiology research, the transition from wakefulness to the N1 sleep stage usually happens gradually. There is no sharp boundary. Electroencephalographic observations show that alpha wave activity decreases, while rhythms in the theta range begin to increase. This change often takes place without being subjectively felt. It is difficult to catch the transition itself at the exact moment, because conscious attention keeps the level of wakefulness somewhat stable. The formation of obsidian also happens as a result of rapid cooling. No observer is required. Thermodynamic and kinetic laws operate on their own course. When there is no time for crystallization, an amorphous structure is formed. The transition to sleep is also a gradual neurophysiological change. Consciousness does not disappear suddenly. The activity pattern is gradually transformed. Biological systems are often silently reorganized, and the results become visible later. Let us look once again at every silicon atom inside obsidian. This atom, a tiny particle surrounded by electron clouds, formed in space billions of years ago. Those atoms drifted for millions of years, combined with other atoms, created clouds. Gravity formed new planetary systems, and some of these atoms fell to the Earth, turning into obsidian within rock and then volcanic lava. Tonight, that atom is in a node of the amorphous network, bound to 4 oxygen atoms. The energy inside the atom, the electromagnetic interaction between the nucleus and the electrons, still exists. From the cosmic processes of billions of years ago to this night. The atoms in your body have also come from the long history of the cosmos. Of course, different atoms, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, but each has its own cosmic history. The energy inside each one is subject to the same physics. Each one is within the framework of the same universal laws. Tonight, you are composed of these atoms. Some atoms were created as a result of cosmic processes. Some atoms, including carbon, were formed as a result of cosmic processes. This is not a metaphor. This is chemistry, astrophysics, a documented, measured, calculated fact. If a thought, an image, a question seemed interesting tonight, you can share it in the comments about obsidian, light, time, or simply about this night itself. There is no need to give any answer. Just leave a trace, put a dot. Perhaps other listeners will see that dot. Perhaps they will find a dot of their own. This night is ending, but the obsidian continues to remain. Tomorrow, perhaps, the sun will rise. Light will filter through the window. Atoms everywhere will continue their work. The magma beneath the earth will slowly move. Somewhere, maybe tonight, maybe tomorrow, maybe 1,000 years later, a new volcano will erupt. New magma will flow. New obsidian will be formed. Again, it will cool rapidly. Again, an amorphous structure will be formed. Again, that black, deep material that absorbs light will form. This process did not start tonight. It does not end tonight. While you sleep, when you wake up, even if you forget this video, it continues. The earth, physics are at work. Atoms are in their places. And you are resting tonight. This is enough. This is all that is needed. Flowing into the depths of sleep, one last image, the peak of a volcanic mountain. Night, the stars visible when looking from the middle of the desert can be seen, not in tens, but in thousands. The sky is in the form of a pillar. That thin band of light of the Milky Way stretches above. The heat inside the mountain is not felt, but it exists. Beneath the ground, magma still exists under heat and pressure. The rocks around the mountain, the pieces of obsidian inside some of them, have shrunk slightly in the cold of the night. The air is motionless. There is no sound, only the faint passing of a distant wind is felt. This moment, the moment of this night, this mountain, these stars, this obsidian, exists. It demands nothing. It expects nothing. It simply exists. You too, tonight, in this moment, simply exist for now. Stay well.